Okay, so the last topic that will be covered in this chapter is equivalence relations. So I've already mentioned this definition before. An equivalence relation is a relation in a set that is reflexive, symmetric, and transitive. Okay, so like I said, relation is an equivalence relation if it satisfies these three things. Now, let me give you some interesting examples. So the example from tutorial 1 satisfies 2 and 3, but not 1, right? It's an example of a symmetric transitive relation that is not reflexive. And the TH probably gave you slightly different examples. I posted my solutions and that has one example. Can you give me an example of something that satisfies 1 and 2 but not 3? Give me a reflexive and symmetric relation that is not transitive. I mean, you can definitely give me one that satisfies 1, 3 and not 2, right? Maybe start with that. A relation satisfying. So I need a relation that is reflexive, transitive, but not symmetric. And finally, so that I prove the independence of all these properties, so a relation satisfying, which one am I missing? 2, okay, I got 2, 3, and so not transitive, right? I guess reflexive, 2, but not transitive is what? You should be able to tell me number 2. Actually, that could have been a good quiz now that I think about it. Let me help you maybe in finding, okay, yes, very nice, very nice. So this relation on, say, the natural numbers is reflexive, symmetric, sorry, what? Reflexive, transitive, but not symmetric, right? It is the opposite, it is anti-symmetric. I just defined that in the very same notes. So now an interesting question is, can you find a relation that is reflexive, symmetric, but not transitive? This one might take a little bit more work, so maybe I can spoil it for you. Let's say that x is related to y if and only if x and y are consecutive numbers. Natural numbers, right? So let me think about this. Okay, to make this reflexive, I think I want consecutive or equal, so less than or equal to 1. This will be symmetric because the absolute value absorbs the order of the sign, right? If this is negative or positive, this won't matter. Okay, now I haven't really talked about subtraction yet, so maybe to avoid confusion, I mean, this example works and it is perfectly fine. An example is on the natural numbers. Two numbers are related if they are equal. They are equal or consecutive. So why is this reflexive? Well, I'm including the possibility of them being equal. So obviously they will be reflexive, right? Every element is equal to itself. Why will it be symmetric? Well, if two elements are equal or consecutive, this clearly the order doesn't matter, right? If x and y have this relation, then y and x have the same relation. They will either be equal or consecutive. One of them is the other plus one, right? But this is definitely not transitive. And you can easily see why. Let me maybe draw this out. So this is 0, this is 1, this is 2, this is 3, this is 4, and so on. So how does this relation look like? Well, 0 is related to itself, 1 is related to itself, 2 is related to itself because all of these are equal. That is obvious. maybe I don't even have the need to write it down because it doesn't really, it only adds to the noise. 0 and 1 are related because they are consecutive. 1 and 2 are related because they are consecutive, and so on. But for example, 0 and 2 are not related because they are not equal and they are definitely not consecutive, right? They're not consecutive because they have something in the middle. So even though 0 and 1 are related and 1 and 2 are related, 0 and 2 are not related, right? So this is not transitive. And now you have an example of each possible combination of these things. If you really wanted to, of course, you could come up with more contrived examples of something that is reflexive, but neither symmetric nor transitive. You can modify the examples I gave here to achieve that. I find that less interesting, right? Because it means you're just going to deal with relations that satisfy fewer and fewer things. Okay. So now that you have an equivalence relation, what can you say about that? So this is a very important definition that I have mentioned before. I have written what it means. I haven't explicitly done that. So let be an equivalence relation on set X. So V for some lowercase x, the equivalence class Do you know what an equivalence relation is? Let me tell you what an equivalence class is. An equivalence class on some element x, and I usually add the subindex for the equivalence relation. When it is clear from context, I drop the subscript and I just write it like this. Right? When clear. What does clear from context mean? It means if in the entire discussion there's only one equivalence relation, well, then I don't really need to specify which one, because there's only one. There's no risk of confusion. But for some exercises, which I don't think will come up ever in this course, we might be talking of two different equivalence relations at the same time. And then, of course, having this subscript to distinguish the sets is necessary. Am I recording? Yeah, I'm recording. Okay. So what is this set? This set is simply defined as the set of all y's in X that are related to Y. Now you might be thinking, this definition makes sense even if this is not an equivalence relation, but just some relation in general. It would even make sense if this were a function, right? If this were a function, then this would be something like the image of the singleton X, or something like that. But there's a deep reason why we only care about these classes, or mostly care about these classes, when we have an equivalence relation. So let me give you an abstract example and then maybe a concrete example. Let me think about this. So here's the idea, and I've made this diagram many times already. So this is, okay, this is X. Give me one